Okay, so let's start. Our topic for today is the fluid flow measurement na Orifice. So last week we had discussed these two fluid flow measurement na pitot tube and venturimeter. And so alam natin kung paano gamitin si pitot tube and venturimeter. Now, ang focus naman natin is si Orifice. Orifice meter. So this orifice meter na nakikita ninyo is instrument siya na ina-attach sa mga pipelines natin to measure the flow or to regulate the flow. So kaya siya bilog dyan yung kanyang figure or yung shape niya, no, bilog. So sa mga pipeline siya ina-attach. And this orifice meter is nagwo-work siya as our parang same as this venturimeter. So, di ba, yung venturimeter, ina-attach din natin siya sa mga pipelines na to regulate the flow and to measure the flow. But we have an orifice na ginagamit din for the tanks and open channels to regulate yung flow and to measure the flow. So, ina-attach yung plates nila. So, plate na yun na parang weirs. Kaso, rectangular, tapos may butas na circular. So, madalas kasi na shape ng orifice natin is circles, katulad na nandito sa mga plates na nakikita ninyo. Ayan, circular, circular, and circular. So, may different sizes tayo dito and classification based on different na classification. Pwedeng according to the size, according to its shape, no? According to the upstream edge, ganun. So, i-discuss naman natin yon lahat dito sa ating orifice. Okay? So, paano ulit, review lang natin kung paano ginagamit si venturimeter, no? Kasi sabi, same sila ng job yung orifice meter. So, ang venturimeter natin, ina-attach sa isang pipeline, then we have a converging and diverging na section wherein from a larger na cross-section, lumiliit tayo, no? Lumiliit yung cross-section. Then, after lumiit, no, we have the throat. After nyan lumiit, babalik tayo sa dati niyang cross-section. Bakit ba natin pinapaliit yung cross-section? Para magkaroon tayo ng changes in velocity and the pressure. So, yung relationship ni velocity and pressure, yung ginagamit natin to calculate the Q using Bernoulli's energy equation. So, si Bernoulli's energy equation, gamit na gamit din naman dito sa dalawang, or hindi, sa weir kasi, iba na yung mga equations natin dyan. So, gamit na gamit siya dito sa tatlong fluid flow measurement natin na pitot tube, venturimeter, and orifice meter. Ayan. So, yun na. Review natin about the venturimeter, no? So, another review is about this device coefficient. So, ginagamit natin to para makakuha tayo ng mga actual na value ng discharge, velocity, and the area. So, we have coefficient of discharge C or CD. Equal yan kay actual discharge divided by the theoretical discharge. And the coefficient of velocity naman, actual velocity divided by theoretical velocity. And for the coefficient of contraction, we have area of the stream or jet divided by the area of opening. Ayan, so madadagdagan later on yung definition natin ng or another type ng kung saan tayo nakakakuha ng area for the orifice, no, actual area for orifice. Ayan. Then, so later na lang, pag nag-discuss na tayo ng orifice, review muna natin to. Then, we have the relationship between these three na coefficients wherein kapag pinag-multiply natin si coefficient of contraction and coefficient of velocity, we have the coefficient of discharge. Okay? So, another review, kailan tayo nakakakuha ng actual na mga values ng discharge and velocity, di ba? Pag makakakuha tayo ng actual values if we consider head loss, di ba? Yung head loss sa Bernoulli's energy equation natin. And also, kapag we have a value from experimentation. Mga values yan. actual kapag galing sa experiment. Ayan. Kapag theoretical naman, saan tayo nanggagaling? Paano tayo nakakuha ng theoretical? Kapag nineglect natin si head law sa Bernoulli's energy equation natin. Yun lang naman. Ayan. So, yung review natin, no, kung kailan tayo nagkaroon ng actual and theoretical na mga values. Okay? So, yun lang naman about the review. Move forward tayo kay Orifice. So, Orifice is another device to gauge the flow of a liquid through a pipe. It consists of a flat plate containing a circular provided eccentricity with the pipe across the flow. It is fitted to the pipe by plunge joint. And this device works on the same principle of the venturimeter. So, venturimeter, ito siya, di ba? We have our pipe, tapos ini-install natin siya sa gitna ng pipe natin between the pipes and yung cross-sectional area natin is pinapaliit natin, no? Para magkaroon tayo ng variation ng velocity and the pressure. Ayan. So, this is our venturimeter. Pinapaliit niya yung cross-section. While sa orifice, paano siya ina-attach? We have our pipes dyan. Pipe natin. Then, sa gitna, nag-i-install tayo ng plate. Orifice plate. Yan. So, side view ito. Yan. Yeah. So, this is our orifice. So, mangyayari niyan, kung may nagpa-flow sa atin na liquid dyan, so, malaki yung cross-section na sakop yan. Tapos, pagdating dito, magkakaroon ng maliit na butas, wherein itong butas na yun, siyempre, dyan lalabas yung liquid natin. So, paano ngayon lalabas? Alangan namang malaki, ito lang yung butas natin. Pag lumabas yan, maliit lang din. So, and this part ng orifice natin, maliit lang yung cross-section ng liquid natin, then later on, lalaki na siya. Diba? Susunod na siya doon sa cross-section ng ating pipes. Ayan. So, in this point, no, right after our orifice, we have changes in the cross-sectional area na fluid na nagpo-flow. And ito yung ginagamit natin to get the Q. Ayan. So, at this point 1, let's say point 1 before our orifice, we have this cross-sectional area wherein the velocity is low. Yung value ng velocity natin is mababa kasi malaki yung cross-sectional area na tina-travel ng liquids natin. Di ba? Pag malaki yung cross-sectional area, velocity is mabagal. Then the pressure is high. Ayan. With this cross-sectional area na malaki, we have larger value ng pressure. And at this point, right after the orifice, where we attach the orifice, we have a smaller cross-sectional area wherein the velocity is high. Mabilis, nagta-travel yung liquid natin dyan. Kasi maliit lang yung cross-sectional area. And the pressure is low. So this relationship of velocity and pressure, ganun din 'di ba yung concept na ginagamit natin for venturimeter. So they work the same principle. Ginagamit natin yung relationship ng velocity and the pressure. Ayan. So, wala naman palang pinagkaiba kapag nakakita tayo ng mga orifice sa mga problems natin. No? Parang venturimeter lang siya. Okay? So, we have different classifications of orifice according to the size. We have small orifice and large orifice. So, from the name itself or from the word itself, large and small. So, sa size lang naman yon. Let's say we have a plate, orifice plate na rectangular, and yung butas natin is like this lang. Mga nag-run ng 2 cm, ganyan, 20 cm. So, we have here a small orifice. Ayan. Tapos, kapag lumaki na, so, syempre, large orifice na yun, di ba? Pag lumaki na yung cross-sectional area ng ating hole, yung butas. Ayan. So, dyan, sa butis na yan, dyan tayo nagka-calculate ng Q. Kapag lumabas na. So, large. Diba? Sa mga problems naman, binabanggit ay small orifice with ganitong dimension, then a large orifice with this dimension, then ibibigay yung mga coefficient of device natin. Ayan. Then, we also have this classification according to shape. So, hindi lang pala bilog yung mga holes natin sa orifice or hindi lang bilog yung orifice natin. May iba't ibang shape siya. And we have the circular, rectangular, square, and triangular orifice. Ayan. So, madalas, ang shape nga natin is circular. Ito yung madalas na ginagamit sa mga problems. And we have this classification according to the discharge condition. We have pre-discharge orifice and submerged orifice. Kailan nangyayari itong dalawang situation natin? Bigay tayo ng tank. So, let's say we have a tank. Na lang nasa sa gilid. So, we have a tank na filled with a liquid. Then, we are asked to solve for the Q na kapag ka nag-attach tayo ng or nag-install tayo ng orifice at the side of the tank. So, kapag meron tayong attached na orifice at the side of the tank, ano mangyayari? 'Di ba? Magpo-flow yung liquid natin pababa. Ayan. So, since wala naman tayong walang sumasalo doon sa nade-discharge na liquid from this tank, we have a free discharge orifice. Okay, free discharge orifice. And kailan naman tayo nagkakaroon ng submerged orifice? So, madalas siya nakikita sa chambers or chamber na tank. Chambers. Or two tanks na magkatabi. Ayan. So, let's say we have these two tanks na magkadikit. Then, initially, nung wala pang orifice na ini-install, yung liquid surface at tank 1 is at this level, and yung nasa kabila naman is mas bababa. Then, when we installed a orifice at the side of the tank, nung connecting these two tanks, anong pwede mangyari sa orifice natin? Yung orifice natin is submerged to the liquid, and kapag inopen natin to, alam natin na yung liquids, gustong-gusto niya na nagpapantay yung level nila. 'Di ba? So, kung ito yung mataas, so sa kanya manggagaling yung flow, okay, para umangat itong isa. So, ito bababa, ito tataas. Ayan. So, in this type ng situation, we have a submerged orifice. Kasi nakalubog yung orifice. Submerged orifice. Ayan. Submerge and pre-discharge orifice. Okay? And we have naman classification according to the shape of the upstream edge. Ayan. So, upstream, big sabihin, siya yung pinanggagalingan ng flow natin. So, let's say in this sample ng submerged orifice, yung upstream natin is itong part na to. And yung edge naman na tinutukoy is yung type ng orifice natin na yung type ng orifice kung paano siya kinat, kung paano tinanggal yung bilog doon or yung hole. Ayan. So, pakita tayo ng figure dyan. And in this figure, we have a sharp edge orifice. So, sharp yung point na to, pointed siya. And kapag in-apply natin siya or in-attach sa mga tanks, yung liquid natin will flow like this. Ayan. So, may onting curvature. Ayan. And in this type of a orifice, we have given values of approximate values of coefficient ng device. Like CC is equal to 0.62. So, zoom natin, no? Medyo maliit. For sharp edge na orifice, we have this approximate value. CC is equal to 0.62. CV is equal to 0.98. And CD is equal to 0.61. Now, sabi ko kanina, 'di ba, for the coefficient of contraction, paano siya kinukuha? We have area na actual, which is from the jet, divided by area ng orifice or opening. Ayan, opening. So, in this orifice, what would be our area ng jet and ano yung area ng opening? So, dito, kapag may lumalabas na sa ating liquid, ang tawag doon sa area ng jet in the orifice is the vena contracta. Ayan, so pag nakita niyo sa problem, the dimension of the vena contracta is ito. Ayan, so yan yung magbibigay sa atin na actual na area ng ating fluid na lumalabas. And this vena contracta is smaller than the area of the orifice or the opening, yung butas natin. So, the area opening is yung dimension ng orifice natin dyan. Okay, so, vena contracta. So, moving on, we have another shape of the upstream edge na square shoulder. And as you can see in the figure, they have the same flow. Kapag sharp edge yung nilagay natin as a orifice and square shoulder, pareho lang sila na magiging flow. So, meaning, the values of CC, CB, and CD will be the same. So, binigay na yung values nila. Ayan. So, 0.62, CV 0.98, CD is 0.61. So, these values of device coefficient was from a series of experiments na gumamit ng sharp edge na orifice and square shoulder orifice. Ayan. So, ito yung mga nila, bigay na values nila. Well, hindi nyo naman kailangan tong kabisaduhin kasi, di ba, nakita nyo naman sa mga problems natin, they're always given, yung mga coefficient of devices. Okay, kung hindi given, makukuha mo naman yung value niyan by the relationships of the actual and theoretical values. Okay? So, another, we have this thick plate. So, thick plate, para siyang square shoulder, pero mas makapal. Ayan. And, paano naman magpo-flow yung liquid natin for a thick plate? Ayan. Tingnan niya yung kanyang flow. So, papasok yung liquid natin from the upstream. From the upstream, papasok siya dun sa butas. Siyempre, kung may nagpa-flow kasi dyan. So, lalabas talaga yung liquid natin. No, hanggat may lalabas ang lalabas. Then, siyempre, magkakaroon mo na yan ng shock. So, we have an air here, sa taas and baba, or sa palibot niyan. Kasi circular yan. Then, right after that, babalik na siya dun sa, or susunod na siya dun sa cross-section ng ating orifice. And so, for this type ng plate na orifice, the coefficient of devices are given na CC is equal to 1.0. Bakit? No, kasi nga, ayan, tignan mo, susunod naman eh. So, yung area ng orifice mo would be equal to the area of the vena contracta. Kasi nga, nagkaroon na ng parang pathway na susundan kasi sobrang kapal ng plate natin. Okay. So, 1.0 is CC, CB naman is 0.86, and CD is 0.86. And so, next, we have the rounded naman na orifice. So, for rounded, the upstream is rounded or part of a circle. Ayan. So, CC would be equal to 1, approximately equal to 1, kasi nga, the area of the orifice, no, opening na orifice natin is equal to the area of the jet or the vena contracta. And for CV, we have 0.98 and CD na 0.98. So, pag grounded, no, halos walang loss or halos mag-equal yung natin, equal yung actual and the theoretical values. So, those are the classification of orifice. Now, let's move on to deriving the equations na ginagamit to calculate the theoretical values of Q, flow rate, and V na velocity. So, pakita tayo ng figure wherein we attach an orifice. Ayun lang natin to. So let's say we have these two chambers, chamber A and chamber B, and this chamber is closed. Yeah, so closed and meron tayong liquid at chamber A with this height, no, with this level, and yung chamber B naman natin, the level is mas mababa doon sa bukas nung orifice natin. Then we have our reference datum as the center of the orifice, no, kung nasaan yung center, nandun yung ating datum. Then, since close ang chamber, we attach gauge pressures, gauge, gauge pressure dito at A and B. Then, so, this gauge will be used to calculate the pressure of air inside our chambers. Ayan. Then, selecting 2 points dito sa ating chamber, we select yung a point na magtatama sa ating datum. So, let's say this point. And yung point 2 naman is right after the orifice or where the vena contracta is known. Ayan. So, yun yung point 2 natin and point 1. So, the flow of our liquid will come from the chamber A papunta sa chamber B. No? Because we have a higher level ng liquid dito sa chamber A. So, di ba, ang liquid natin, kung hindi yan pantay, gusto niyan magpapantay silang dalawa. So, magpa-flow yan, papaba. Okay? Then, we have this distance, na initial distance ng liquid natin at chamber A as H from this reference datum. Ayan. So, to relate the point 1 and point 2, we can use the Bernoulli's energy equation or the BEE, wherein energy at point 1 must be equal to the energy at point 2 in this situation. So, sabi ko nga, theoretical na values yung i-derive natin dito. So, we will use the Bernoulli's energy equation na neglecting the head loss. So, E1 is equal to E2 lang. Wherein, E1 is the summation of the potential in the kinetic head at point 1 and the point 2 naman na E2 is the summation ng potential and kinetic head natin. So, let's investigate the variables here na V1, P1, Z1, V2, P2, and Z2. So, V1 natin would be the velocity na nararanasan at our chamber A. So, let's say that is VA. So, we have VA squared over 2G. Now, for the P1, ano yung pressure na nararanasan natin at this point 1? So, ang nararanasan natin dyan is the summation ng pressure ng air at here, na pressure ng air, plus the pressure due to the liquid. Diba? So, we have here the pressure sa liquid due to the liquid na in an equation ng unit weight times this height na h. Ayan. So, we have PA plus this P or unit weight h over h. Ayan. So, contribute yan yung air pressure natin. Then, our Z1, since our point 1 is in the datum, so 0 yung Z1 natin. Then, for V2, V2 is the velocity measured by our orifice. So, let's say V2 is equal to V. So, we have V squared over 2G. And for point 2, the pressure is exposed sa air and since we are gauge pressure yung P natin sa Bernoulli's energy equation, due to the air na lang yan. Wala na yung due to the liquid na unit weight H. So, P2 is equal to the PB measured by the gauges here. PB over gamma and Z2, like sa Z1 natin, natatama yun sa datum. So, 0. Ang matitira sa atin is an equation na VA squared over 2G plus PA over gamma plus H na lang, no, pinaghiwalay natin, equal to V squared over 2G plus PV over the gamma. So, we will solve for the equation of velocity measured by the orifice. So, let's transpose this PV over gamma doon sa kabilang side na equation. So, we have V squared over 2G equal to VA squared over 2G plus PA over gamma minus PV over gamma plus PH. Then, solving for V, so, multiply both sides ng 2G, then square or apply square root both sides. So, we have V equal to square root ng 2G multiply to the H plus BA squared over 2G plus PA minus PB over gamma. So, in this bracket na, naka-bracket na equation, meron siyang kamukha, di ba? So, para siyang summation ng mga head natin that produce the flow. So, actually, yun. Siya nga yun, no? That is the total head producing the flow. So, we can write this in a single variable, which is H. So, this H means na siya yung total head producing by the flow na equal dito sa H plus BA squared over 2G plus PA minus PB over the gamma. So, in books, makikita nyo, equation kapag may orifice is this one. No? Velocity theoretical is equal to the square root ng 2G H. But you have to take note of this H. Yung H mo, hindi yan basta height lang dyan sa orifice mo. Yan yung total head na producing the flow, which is equal to this one. H plus BA squared over 2G plus PA minus PB over gamma. So, kailan lang siya magiging variable na H? Kapag wala kang BA, wala kang PA, wala kang PB, no? Kasi zero sila. And yung matitira is H na lang. Ayan. So, let's go on to the various na conditions ng H natin. No? Kailan nagkakaroon ng velocity and PA and PB, no? So, hanap tayo ng mga samples natin. So, values of H for various condition. We have a pre-discharge orifice. Mag-investigate tayo ng pre-discharge orifice. So, let's say we have an open tank. Open tank. Ayan. With this level ng liquid, and we attach an orifice at the side of this tank, and given tayo ng points dyan na ganun pa rin. Ito, yung ginamit natin is yung sa datum. Okay, so we have this point 1, then yung point 2 naman is ito. So, we can use yung derivation natin na yan. So, we will solve for the value of H. Ayan. So, in this problem or in this figure, we have an open tank. Open tank, yan. So, kapag open tank, yung pressure natin at the top is 0. So, kasi gauge pressure. So, 0 yan. So, meaning, yung P1 na yan is yung PA, diba? So, kung 0 yung P1, 0 yan. Ayan. And at point 2 naman, so exposed sa air, no, wala siyang, kasi may katulad dito sa chamber B natin, closed siya. And ito yung nakakalculate natin na pressure na gauge. So dito, exposed sa air, so meaning yung P2 din natin dyan is 0, which is PB in our equation. So 0 din yan. And we are analyzing a tank. Ayan. 'Di ba kapag tank, yung ini-investigate natin and we have a small orifice na sobrang liit kaysa dun sa tank natin. Yung pag-low or pag-rise ng liquid natin inside the tank is very negligible or hindi natin ganun na nakikita. So, meaning the velocity inside our tank, which is the VA, is almost 0 na. So, in this equation for H, no, yung VA ay 0. So, ano matitira na value ng H natin kapag open na tank? No? Ang matitira is H na lang, which is the head ng liquid hanggang dito sa gitna ng orifice. So, that is the head of the liquid. Head is equal to this H. The total head is equal to H. And paano naman if we have an open tank na moving? So, na-discuss din nyo ito during your fluid mechanics wherein you have the rectilinear na motion ng fluids na nag-move to the left or right, up and down. And so, you have derived the equations and yung mga assumptions. Okay? So, for this type ng problem, ang bago lang is mag-attach tayo ng orifice. And we are solving for the value of the total head producing the flow. So, in this type of figure or problem, the value of H is equal to the H times 1 plus minus A over G. So, alam nyo na to kung kailan nagkakaroon ng positive na acceleration and negative acceleration. Ayan. So, ito yung equation natin dyan. So, di ba, during your fluid mechanics, that is in terms of the pressure. But now, that is in terms of the pressure head. Okay? And next sample natin is when we have a closed tank. Closed tank naman siya and free discharge pa rin. So, our variables would be the P1 kapag closed tank, that is equal to P. Then P2, since exposed sa air, that is equal to 0. And we have the head of our liquid na H hanggang sa orifice natin. Okay. And the unit weight of the liquid here is gamma. And for this type, the total head is equal to, ano kaya yung value niya? So, balik tayo dito sa equation natin ng H. Yeah? So, ganun pa rin, yung point natin is here. Kasi yun yung ginamit natin sa pag-derive nitong equation na to. Yung ginamit nating datum is yung sa gitna ng orifice. So, hindi pwede na yung datum mo magiging nasa taas, di ba? Yan. Kasi sa isang Bernoulli's energy equation, isang datum lang dapat yung ginagamit mo. Hindi ka lumilipat-lipat. Yeah, so, this will be our point 1. Ito naman yung point 2 natin. Or, layo. Meron contractant dito. Ayan, so this would be our point 2. Ayan. So, going back, no, we have the value of H. May head yung liquid natin hanggang sa orifice, that is H. Okay, then the velocity at point A or inside the tank is 0 na since this is a tank. No? Velocity is 0 there. Then, PA is due to the pressure ng air dyan. And since close yan, so may value si PA. And that is equal to this P. Ayan. And PB naman is yung pressure natin at point 2, which is exposed sa air and equal to 0. So, ano na lang matitira? We have H plus P over gamma. No? Have to take note that yung P dyan is yung pressure doon sa inside the tank. So, H is equal to H plus P over the gamma. So, lahat naman sila galing lang sa Bernoulli's energy equation. Okay? And paano naman kung meron kang closed tank and we have an applied na liquid na dalawa, magkaibang unit weight or magkaibang specific gravity. Okay, so have this condition. So for this condition, and gagamitin natin yung relationship ng specific gravity and the height, no, which is SG or yung saha-baha. Ayan. Okay, so kinabisado ko siya dati as saha-baha. S-A-H-A is equal to S-B-H-B. Ayan. So, gagamitin nyo ito sa pag-calculate for the total head dyan, ayun, in terms of the pressures, in terms of the pressure. And madiderive nyo itong equation na to. So, H, the total head producing the flow, is equal to the H2. Yung H2 is the height ng liquid, no, at the bottom hanggang sa orifice. Then, plus H1, which is yung liquid to liquid surface nung liquid na nasa taas, then unit weight 1, unit weight na nasa taas, then divided by the unit weight 2 na nasa baba. And plus the pressure divided by the unit weight na nasa tapat nung orifice natin. Yan. So, then, next, we have this orifice for a submerge. Submerge naman na orifice, which is parang ganito lang din nung nasa chamber natin dito. Kaso lang hindi nakasubmerge yung orifice natin. But now, isasubmerge na natin siya. Yung, aabot na yung water level or liquid, yun, yung liquid natin dito sa taas ng orifice. So, derive natin yung equation for that. So, let's say we have this figure. Ayan. We have this distance ng level here hanggang sa orifice na H1 and yung liquid naman, liquid surface dito hanggang sa orifice is H2. And the change in water level or liquid level is H, yung kanilang distance. So for this, the total head sa submerged orifice is equal to the H1 minus H2 equal to H. Ayan, ito yung H natin. Ayan. Yan yung value ng total head natin sa iba't ibang condition. Free discharge, open or closed na tanks, and for submerged orifice na dalawang magkatabing tanks. Ayan, na next. Okay? So, ito naman yung mga conditions dito will be, magagabay nyo siya kapag in-apply na natin sa problems. Okay? Yan. So, later, apply natin sa problem. And yung H na yan, sinasubstitute natin dito sa value ng theoretical velocity para makuha natin yung value ng theoretical velocity. Okay? So, we also have this sample na or problems under the orifice about the unsteady flow. Kailan ba tayo nagkakaroon ng unsteady flow? Nagkakaroon tayo ng unsteady flow kapag nagba-vary yung head natin. Yung head H or yung total head na producing the flow. And also kapag nagba-vary yung cross-sectional area of our tank. Yeah, so we had discussed the meaning of a unsteady flow no during our first meeting. No, diniscuss natin yung different types ng flow natin. So unsteady, iba-iba yung Q natin at different points ng pipes natin or streams. Ayan. So, let's say we have a tank na, draw tayo ng tank no. Balikan natin. We have a varying cross-sectional area ng tank. So, kapag kumuha ka ng area at this point, iba yan at another point ng mga tank mo. So, if you're going to calculate for the Q at point 1 and this point 2, magkaiba yung value niyan kasi iba yung cross-sectional area natin. Okay? And paano naman tayo nagkakaroon ng varying na head? Nagkakaroon tayo ng varying na head kapag halimbawa nag-install tayo ng orifice at the side of our tank. So, our tank will withdraw or yung orifice natin will withdraw yung mga liquids inside the tank. So, let's say yan dito yung water level natin. So, water na lang yung liquid natin. So, lalabas yan, pababa. And, varying siya, bali yung H natin kapag nagkaroon ng pagbaba or pagtaas yung liquid natin. Kailan nagkakaroon ng pagtaas? Kapag meron din tayong in-apply na Q in or may pumapasok sa atin na flow. Q in. Ito naman yung Q out natin. So, pag may pumapasok sa atin na flow, dito, depende yan kung malakas siya or mahina. So, kapag malakas yung flow natin na pumapasok, pwedeng magkaroon tayo ng rise. So, pwedeng umangat siya at this level. Pero pag mababa yung QN natin kaysa doon sa outflow dito sa orifice, pwede tayo magkaroon ng pagbaba inside our tank. So, nagbabari yung head natin due to time and this orifice. Yan. So, ang madalas na kinakalculate for this unsteady flow orifice is yung time. So, let's say we have this original na head no, from our orifice. Ito siya. So, we have this original head H1. Ayan. And, ang problem here is how long will it reach yung water level natin will reach at this level na H2. Yan yung madalas na mga questions here for the unsteady flow orifice. No? May kinalaman sa time. Kung kailan siya makakapag-withdraw ng ganitong level ng liquid no, inside the tanks. Ayan. So, we have derived equation for this. And for different conditions, kapag may inflow and may outflow. So, pakita natin yung derivation. So, unahin natin yung tanks na may varying cross-sectional area and the outflow is through an orifice then with inflow. Ayan, so we have here yung tank kanina Yan. And we have an inflow and outflow through an orifice and varying yung cross-sectional area of our tank. So, originally, we have this head 1, H1, ng head ng ating liquid hanggang sa orifice. Then, our final na head, after natin mag-release ng liquid, is this one, H2. And for this type ng tank, we have to calculate for all of the Q na nandito sa tank. So, kung kailangan natin silang i-add up, ano yung gagamitin natin na equation? So, may kinalaman si calculus. Kailangan natin kung kailangan natin i-sum up yan, kailangan i-integrate natin yan from this level hanggang dito, no, para malaman natin yung Q nila na nailabas. So, let's have an equation of the Q na dapat in differential or integral na calculus. Dapat integral kasi sum eh. So, from Q, yung Q natin na equation, di ba, Q is equal to the area times the velocity. Ayan. Kaso, sabi natin dapat may kinalaman yung time natin dito and the cross-sectional area. Kailan tayo nagkakaroon ng equation na yun? So, we have the volume, no? Q is also equal to the volume over the time. So, ito pala yung mas magagamit natin na equation for the Q in this type ng problem. Volume over the time. Wherein, yung volume mo dapat in terms of the area and this head H. Ayan. So, we have AS, di ba, at this H, or we have, kung small part lang ng tank natin yung kukunin, dapat in terms of a differential or integral na calculus. So, AS or volume here will be equal to the AS times the H or AS VH. So, sige, sulat natin siya mathematically. We have Q is equal to dV over dt, wherein V here is the volume and dt naman is yung sa equation natin for the time. And the total Q in this sample would be equal to the Q in minus Q out. No? Madadagdag minus yung nababawas. Yan yung total Q natin. So, let's write this equation and solving for the time. We have dt equal to dV over Q in minus Q out. And we have to take note that dV is equal to the AS times the DH. So, nagba-vary yung area natin as we go down or as we go up. Kasi vary yung cross-section natin. So, yung height is another, or we will have an equation of AS in terms of H dyan, no, kung varying siya. Okay. So, palitan natin si dV na AS, DH. Yan, dt is equal to AS dH over Q in minus Q out. And for us to get the total time para ma-reach nyo itong level na to na H2, we have to integrate both sides of our equation. So, integrating dt, we have T, and integrating naman yun nandito sa right side ng equation natin, that would be an equation, no? And the limit would be from H1 to H2. So, upper limit is H2 hanggang H1. Yan. So, this would be the equation na gagamitin natin kapag may inflow and nagba-vary yung cross-sectional area of our tank and mayroon tayong outflow through an orifice. Ayan. So, paano kapag wala namang inflow? Ayan. Kung walang inflow, dito lang din sa equation na na-derive natin, wherein Q in is equal to 0 na. So, matitira is integral ng AS dH over negative Q out. The limits will be H1 hanggang H2. Ayan. So, for this equation, ang makukuha nating value ng time is negative. Eh, di ba wala naman tayong negative na time? So, we can manipulate this equation then magkaroon tayo ng positive value of time. So, pwede natin pagbalik na rin yung limits natin. So, we will have ASDH, Q out, no, H1 and H2. So, our upper limit will be H1 and the lower limit is H2 for us to get a value ng time na positive. So, that would be the equation for a varying cross-sectional area and may outflow, walang inflow. Ayan. So, kailangan na kabisa or gamay nyo pa si integral calculus sa mga problem na ganito sa hydraulics. Ayan. So, magko-combine sila. Ayan. So, paano naman kapag meron tayong tank na constant naman yung cross-sectional area niya. Tapos may outflow pa rin pero walang inflow. Ayan. So, kapag ganun, constant na yung cross-sectional area natin as like this in this our figure, say we have a cylindrical na tank. So, at different point, so initially kung ito yung head natin, kapag bumaba, pareho pa rin na ES yung area natin. Siya kasi constant eh. So, pwede nating magamit for the derivation is this equation, yung walang inflow. And we will cancel out yung sa integral na sign kasi nga yung cross-section natin is constant. So, derive natin. Wherein yung Q out natin is from the orifice. So, Q out is equal to the area nung vena contracta dyan. So, area ng vena contracta. Kasi nga, orifice eh. So, area ng vena contracta times the velocity of the liquid na actual na lumalabas dito sa ating orifice. So, that would be our Q out. So, paano natin nakukuha yung value ng Q out dito sa mga gantong problem? So, madalas, na-given kasi dyan is the area of the orifice. Ayan. Area of the orifice and the head. Ano yung value ng head natin na H. So, we can write this equation ng Q out to, diba? So, area ng vena contracta, may relationship yan na equal siya sa CC times the V or the area ng orifice. Ayan. Kasi area ng orifice lagi yung given. And for the actual naman na velocity, may relationship yan with the coefficient ng velocity. Then, multiply to the theoretical na velocity. And we had derived the equation for theoretical velocity for an orifice that is square root ng 2gh. H is the total head producing the flow. Yan. So, kailangan alam natin yan kung paano gamitin yung H. No? So, na-discuss naman natin yan kanina. So, lagay natin si VT dito for us to get the actual velocity. So, we have CV multiply to square root ng 2GH. So, substitute natin yung area ng vena contracta and equation natin ng velocity here. So, we have CCAO multiply to CV square root ng 2GH. So, wherein, itong CC and CB, di ba alam natin na yan ay equal kay coefficient of discharge. So, we can simplify this equation by CAO square root ng 2GH. Ayan. So, ito yung equation natin kapag meron tayong orifice and we have to calculate for the flow rate. Ayan. So, magagamit nyo din to sa kahit anong problems natin about the orifice. Then, required na hanapin yung discharge sa ating orifice. No? CAO square root ng 2GH. Ayan. So, ayan. Dito na siya sa ating equation. So, substitute natin yan dito sa equation natin ng time. Okay. Equation ng time wherein we have the H1 and H2 integration ASDH over Q out. Substitute yung Q out, we have this one. And pwede nating ilabas dito yung mga constant natin na value. So, constant si cross-sectional area, no, yung AS. So, pwede natin ilabas yan. And also, CAO square root ng 2G, yan ay constant. O, matitira na lang sa atin dito is yung square root ng H sa equation. So, we have this one, integral ng dH over square root ng H. Limits natin is H1 and H2. And, kailangan natin i-integrate itong square root ng 1 over square root ng H. Yan. So, parang hindi mahirap yung equation, pwede natin itaas si H. Ang mangyayari, we have negative, no, H raised to negative 1/2. Ayan. Then, we can simply integrate this equation, no, wherein we have H negative 1/2 plus 1, no, divided by negative 1/2 plus 1. Integrate nyo lang yan. So, to simplify, ang mangyayari, we have negative 1 half plus 1 half, yan ay raised to 1 half. And then ito, may 1 half din. Okay? So, yung 2, dahil nasa over, tataas yan. So, we have 2h raised to 1 half. Ayan. So, mawawala na yung integral natin na sign dito. Magkakaroon na lang tayo ng limit sa gilid. So, burahin ko na tong derivation for the Q out. Ayan. So, we have this simplified na equation na 2h 1 raised to 1 half. Yung limits natin is h1 and h2. So, for us to solve for the time, we have to substitute the value of h1 dito sa equation. Then, substitute din yung value ng h2. Kaso lang, di ba, we have the upper limit minus the lower limit. Hindi mo sila basta isa-substitute na ipag-add. So, upper limit minus the lower limit. And for simplification, the equation for the time for a cross-sectional area na constant and may outflow through an orifice is, ayan, we have 2as over CAO square root ng 2g multiplied to the square root ng h1 minus square root ng h2. So, yung 2, dahil pareho naman yan meron, no, pinactor out natin, tapos inilabas na. So, dito lang naman yun galing sa equation na ito. Ayan. So, kahit hindi mo i-derive, ito na lang. Kaya naman yan, kabisaduhin. Basta, lagi mong ginagamit sa mga problems. Ayan. So, these are the equation for unsteady flow, orifice na free flow. So, meron pa tayong submerged na flow. Ayan. So, medyo mahirap siyang kabisaduhin. Okay? Pero, kaya nyo yan. Practice lang. So, for the unit of time, kung magtatanong kayo, ano, ma'am, yung unit ng time mo dyan? Sige, derive natin yung unit. So, for area, kung SI tayo, that is meter square meter. Then, C is the coefficient of discharge, which doesn't have a unit. No, unitless yan. Wala tayong problema. Itong area ng orifice, in terms of SI, we have square meter. Then, inside the square root, we have meter per second squared. So, we have square root ng meter per second squared. Then, here naman, we have square root ng meter. Yeah. So, magka-cancel out si square meter. And magka-cancel out din yung square root ng meter. Ayan, then yung 2 dito na raised na s natin since naka-square root yan, that would be canceled out na. So, matitira is 1 over 1 over s. So, si s, aangat sa taas. So, meaning, the unit of time here is in seconds. In seconds yan. Yung time natin dyan. Ganon din naman kapag English, no, seconds din yung madederive natin na unit niya. Ayan. So, marami-rami na ba kayang nalilistang equation for the orifice? Yeah, marami pang darating. Sige. So, derive pa tayo ng equation for a submerged na orifice. Sabi lang natin tong mga equation na yan. Bakit? Mas maganda kung nakikita natin silang sama-sama eh. So, we have tanks connected by a submerged orifice. Ayan. And, ganun din yung problem dito. No? So, initially, the situation of our tank, ganito yung water level natin. So, let's say water na lang yan since blue yung liquid. So, initially, we have an head 1, each one. Ayan, kapag close pa yung orifice natin. So, pwedeng tube din to, pwedeng orifice. Ayan. So, same sila naman ng purpose. So, initially, this is our H1. Now, nung inopen natin yung orifice natin or the tube, no, nagkaroon tayo ng pagbaba at tank 1, then pagtaas naman sa tank 2. No, we have the volume lost at tank 1 and volume gained at tank 2. So, for this type na situation, we are asked to determine the time for these two tanks reach this difference na water level na H2. So, we can solve for that time using this equation na 1 over CAO square root ng 2G integral ng AS1, AS2 over AS1 plus AS2, h raised to negative 1/2 from H1 to H2. Yeah, DH. There. So, this is for calculating the time kapag ka yung cross-sectional area of our tanks ay varying. Yan. Paano kapag hindi naman nagba-vary yung cross-sectional area natin? So, we can use yung equation natin na wala ng integral na sign. So, that would be AS1, AS2 over AS1 plus AS2 multiplied to 2 over CAO square root ng 2G square root ng H1 minus square root ng H2. Well, kung nabibigla kayo sa ano natin sa equation for the time, actually parang pareho lang yan nandito sa isa. Yan yung kapag isang tank lang. Ayan, so we have 2AS over CAO square root ng 2G. Pareho sila dito ng multiplier, but yung AS natin for 2 tanks ay may verification or merong modification na for AS2 din. Ayan, so kailangan ano sila, magko-contribute yung cross-sectional area mo ng tank 1 and tank 2 here sa time na yan. But the unit for the time here is pareho lang in seconds. So, sige, derive natin. Diba dito we have meters, square meter, dito din square meter. Unit natin dyan. So, mag-multiply ang dalawa. Yung sa baba, meron tayong square meter lang. Then ito, square meter. And then here we have a square root ng meter per second squared. And dito we have square root ng meter. So, magka-cancel si square meter. Cancel din to. It is 1. Ito, yung square root ng m ng meter. Cancel. Then yung squared sa seconds natin will be canceled out. And seconds will go up to our equation. So, the unit for time here is in seconds. So, pwede niyong gawing way ng pagkabisado ng formula yung sa units. Kailangan tama yung maging unit mo para maging tama yung equations. And, yun. So, pwedeng, yun, gawing way na sa pagkabisado is yung unit na lalabas. Yeah. So, for time, dapat seconds yan. Okay. And paano ko nakabisado tong equation na to during the undergrad? Ano lang, nag-practice lang ako ng problems na calculating for the time sa mga orifice na nagpo-flow. And so, ganun din ninyo yan makakabisado guys by practice. Pag lagi nyo siyang ginagamit, hindi kayo mahihirapan sa pagkabisado niya. And also, may part din yung halimbawa nag-exam kayo, tapos, syempre, nung face-to-face na class, di ba, bawal naman may index card kapag may exam. Then, meron kayong exam na, ang tanong is about the time. So, pag na-meet nyo yung ganong problem, tapos nang hinayang kayo sa kanya kasi hindi nyo kabisado, the next time na itatake nyo yung question na yun, alam niyo na siya kasi nga nang hinayang kayo sa kanya, 'di ba? Hindi niyo na nasagutan. Yan. So may part din na gano'n, parang magka-comeback ka kasi kaya kitang kabisaduhin pero that time hindi kita nasagutan, ngayon kailangan masagot kita, 'di ba? Yan. And also etong mga equations naman na na-derive natin about the Orifice, kapag in-apply na kasi siya sa problem, kaya ka manghihinayang, no, na hindi mo siya nasagot, is direct substitution lang. Kapag meron ka ng mga given na problems, tapos kabisado mo yung equation, direct substitution lang ng mga given sa problem. Yeah. So, ang kalaban mo lang talaga dito is yung pagkabisado ng equation. And kailangan nyo siyang kabisaduhin, guys, yung mga equation na to. Kasi, madalas tong lumalabas sa board exam. Ayan. So, maganda ngayon pa lang, kabisado nyo na yung mga equation na to para pagdating na magpe-prepare na kayo ng board, unti na lang yung kakabisaduhin nyo kasi halos lahat ng equation under the hydraulics and fluid mechanics, alam nyo na. Diba? So, onti na lang yung kakabisaduhin nyo. Yun na lang yung parang mga nadagdag na formula from different researches na bago lang, no? Kasi lagi namang merong nai-invent or nade-derive ng mga equations through experiments. Tas mga biglang lumalabas, ayan. So, that would be given by the review centers na. But for now, ayan, kabisaduhin niyo yung mga binibigay sa inyong mga equation para onti na lang yung magiging adjustment ninyo for the board. Okay? So, wala pa 'to, onti pa lang 'yan guys. Meron pa tayo sa mga susunod natin na topics and also dadagdag niyo pa yung sa formula sheet niyo yung for the geotechnical engineering. So, hydraulics and geotechnical engineering kasi is the subjects na puro formula and the formula there is empirical, meaning you can't derive it. For the Orifice naman, nade-derive natin pero later kapag nag-weir na tayo, we can't derive the equation anymore. Kakabisaduhin na natin siya and ang dami niyang mga values na nasa unahan, 'di ba? So, mahirap kabisaduhin kapag yung equation mo may mga numbers na, 'di ba? Buti na kung mga number na nasa tapat niyan puro 143, di syempre madali siyang kabisaduhin. Eh, hindi. Merong 1.859 ganyan. Merong 1.84, may 1.4, meron pang 0.5518. Diba? Parang mga kabisado yan, mga decimal, may mga decimal places eh, di ba? Eh kung 143 lang, eh, di ba? Ang daling kabisaduhin yan. Ayun. So, hindi ganyan. Kasi nga, empirical na equations. And, kapag empirical na equations, no, may mga problema tayo sa empirical equations kasi yung mga value pala yun na constant ay may unit. Later, makikita nyo yan sa weir natin. So, investigate natin yung formula for the weir. So, orifice muna tayo. Ayan, may tanong ba kayo about the derivations of equation here sa orifice before we apply it to the problems? Wala naman. O sige, apply natin sa problem. Kaya natin, we have a lot of problems na i-discuss this day. Ayan. For problem number 1, calculate the discharge in liters per second through a 100 millimeter diameter orifice under a head of 5.5 meter of water. Assume CC is 0.61 and CB is 0.98. For this problem, we don't have a given na figure. Ayan. Pero, kaya naman natin yan i-drawing given na meron tayong problem. Ayan. So, madalas, yung orifice natin is ina-attach sa mga tanks. So, we have here a tank. Yan. Then, ito yung orifice natin attach sa side of a tank. And sa problem natin, we have this given head, no? Given head na 5.5 meter. And that head is measured sa gitna ng orifice natin hanggang doon sa liquid surface. So, our liquid is a water. So, water surface. 5.5. Yeah, 5.5 meters. So, water yan. And yung dimension ng orifice natin is 100 millimeter diameter. Yeah. CC, coefficient of contraction, 0.61. CV, coefficient of velocity, 0.98. We are asked to solve for the Q in liter per seconds. No, liters per second. Kapag Q, alam natin yung equation natin ng Q, that is area times the velocity lang. Wherein, the area must be in actual and the velocity must be in actual. So, actual area is equal to the CCAO and the actual velocity is equal to CV square root ng 2GH. So, this equation, sa derive natin to kanina, di ba? Pag multiply natin, so we have yung Q na equal to C square root CAO square root ng 2GH. But in this presentation, hinimay ko yung solutions. So, I solve for the value of A muna and solve for the value of B and then later on multiply the two values for us to get the Q. Ayan. So, gawin natin yung procedure na yon. But, since alam niyo naman na tong equation ng CaO square root ng 2GH, pwede na yang direct na isolve dyan. Sige. So, Cc, we have 0.61. AO, that is the area of the orifice. We have this dimension ng orifice na 100 millimeter. So, since bilog yan, our area would be pi d squared over 4. And yung diameter natin must be in meters. Okay, meter. So, convert 100 millimeter to meter, that is 0.1. We have pi over 4 times 0.1 squared. Simplifying, the actual area is 4.791 times 10 raised to negative 3 square meter. Then, for the velocity na actual, we have CV 0.98 square root ng 2G. No, 2 times 9.81. Yung G natin must be in SI, which is 9.81 meter per second squared. Ayan. Then, our H, since we have a free flow lang naman, no? Free flow yan. Di ba? Na-derive natin na yung pag free flow, open na tank. Kasi wala naman sinabing close yan. So, open na yan agad. Our H is equal to the head of our water, which is 5.5. So, lagay lang natin dito yung 5.5. So, simplifying, our actual value is 10.180 meter per second. So, multiplying these two values of A and V, the Q is 4.791 times 10 raised to negative 3 times 10.180 or 0.04877 cubic meter per seconds. Eh, ang required sa atin na unit is liter per second, so we have to multiply 1,000 liters per 1 cubic meter. So, the answer would be 44.77 liters per second. So, di ba? Direct substitution lang siya. So, may question po ba about problem number 1?
Wala.
Okay, sige. Proceed tayo. Problem number 2. Ayan. So, calculate the discharge through the 140 millimeter diameter orifice shown. Assume C is equal to 0.62. Okay. So, we have this chamber na ginamit natin kanina for the derivation ng equation for theoretical velocity and for H. Ayan, so magagamit natin yan dito. So, we have to take note that the points na ginamit natin during the derivation ay andito sa datum natin. Ito yung point 1, ito naman yung point 2. Ayan. So, kung discharge yung kailangan natin i-solve, di ba? Q is equal to AV lang, or Q is equal to CAO, square root ng 2GH, since orifice naman yung instrument natin dyan. Wherein, the H is equal to the total head producing the flow. H plus B1 squared over 2G plus P1 minus P2 over the gamma. Ayan. So, solve natin yung value ng H no, para magamit natin sa pag-calculate ng discharge. So, H is the head of the liquid hanggang sa orifice. So, that is given in this figure na 3 meters. Ayan. Lagyan natin ng value, 3 meters. Velocity at point A. So, this is a tank. No? So, velocity there is almost approaching to 0. So, velocity there is 0. Ayan. So, wala yan sa equation natin. Then, closed tanks naman to. So, meaning we have pressures due to the air calculated by these gauges. So, our P1 is equal to PA and equal to 50 kilopascal. Then, yung P2 naman natin ay 15 kilopascal. So, in kilopascal, so, para maging meter, dapat makancel si kilonewton per square meter. So, the unit for kilonewton must be in for the kilonewton. For the unit weight, must be in kilonewton per cubic meter. So, ano yung unit weight natin for water in kilonewton per cubic meter? So, that is 9.81, diba? So, divide lang pala natin yung 50 minus 15 sa 9.81. So, simplifying, our H, no, total head producing the flow is 6.568 meters. Yan. So, we have to substitute this H dito sa equation natin, no, for Q. So, natin, C is 0.62. Okay. So, C is 0.62. AO naman is pi over 4 times 0.14 squared, which is the area of our orifice given by this diameter na 140 millimeters. So, converted na yan into meters. Then, square root ng 2GH. G natin is 9.81, H is 6.568. So, the Q is, ayan, nauna na, no, may answer na agad si, wala na pangalan. Si Benedict, may answer na agad. That is 0.108 cubic meter per seconds. Ayan. So, this would be our answer for this problem. So, you have to take note of the values of H. Na hindi lang siya basta head ng water natin. No, nagkakaroon ng variation niya sa pressures natin and the velocity. So, madalas naman sa tanks ina-apply yung Orifice, no, yung mga problems natin dito, nasa tank siya. So, yung velocity is 0 na. Kasi mas malaki yung cross-sectional area ng tanks natin kesa sa cross-sectional area ng mga orifice. Okay? Sige, proceed tayo kay problem number 3. Ayan. For problem number 3, a 50 millimeter diameter circular sharp edge orifice, the side of a tank, discharges water under a head of 3 meters. If the coefficient of contraction CC is 0.63 and the head loss is 240 millimeter, compute the discharge, calculate the coefficient of velocity, calculate the coefficient of discharge. Ayan. So, Q, C, V, and T. Yung hinahanap sa atin. And given yung dimension ng orifice, 50 mm. Ayan. And CC, given din, 0.63. Head ng water. Water yan. Ayan. Tama. 3 meters, given naman. And we have this head loss. Ayan. So, saan kaya natin gagamitin si head loss? Or head loss? So, gagamitin natin to for us to get the actual values of discharge and or velocity. Ayan. So, let's start our solution by solving for defining our points na point 1 and point 2. So, for now, hindi natin gagamitin yung point natin na nasa gitna ng orifice, yung datum natin. Hindi natin siya ipipick dyan. Or, hindi natin ipipick yung points natin dito sa datum. So, ito pa rin yung datum, pero yung location ng points ay ibahin naman natin. Yeah? Kasi may different way naman tayo ng pag-solve it. So, our point 1 would be this one. Ay, nandun. Then, yung point 2 naman is ito. Ayan. So, ito yung 2 points natin. Ano mo ba? Then, gagamitin natin yan later on, no, sa pag-calculate ng actual na velocity, no, using this head loss na 240 mm. But for now, let's solve for the actual area. So, the actual area can be solved by the given CC and given diameter of the orifice. So, CC is equal to the area na jet, area ng vena contracta divided by the area of the opening or area ng orifice. So, we have 0.63 na CC and the area ng orifice is pi over 4 times 50 over 1,000 squared or 0.05 squared. Yan. So, yung area natin dito, that is for the actual, di ba? Ayan. So, dati sinusulat din natin to as small a tapos divided by larger a. Ayan. So, wala namang problema dyan kasi variables lang yan. As long as you have here sa taas na actual, yung baba, theoretical. Okay. So, solving for the actual area, we have 1.237 times 10 raised to negative 3 square meter. Actual yan. Then, we have theoretical na value ng area natin. The theoretical area is given by the Orifice. So, that is pi over 4 times 0.05 squared or 1.963 times 10 raised to negative 3 square meter. So, gagamitin natin to later sa pag-calculate ng discharge. So, dyan muna natin. Then, solve for the actual velocity. Kasi Q is equal to AB, di ba? So, we have to get the actual area and the actual velocity. So, we can get the actual velocity by the Bernoulli's energy equation considering head loss na 240 millimeter. So, we have E1 minus HL equal to E2. So, E1 is yung summation ng kinetic and potential head natin. Then, yung E2 naman is summation ng kinetic and potential heads. So, investigating our point 1, yung B1 natin dito, since nasa tank, that is 0. Diba? So, wala. The P1, since exposed sa air, yung point 1 natin, that is also cancelled out sa ating equation. Then, Z1, that has a value. Na elevation ni point 1, papunta sa datum natin, that is 3 meters. So, may value siya. Then, HL, may value, 0.240. The velocity 2, that is the velocity na nasa jet natin. So, yan yung ginagamit natin to solve for the velocity na calculated by the orifice. So, B2 is B. Then, P2, since exposed sa air, that is also equal to 0. Then, yung Z2 naman, nasa datum natin, so, 0 din. Wala siya sa equation natin. Matitira is Z1, HL, and yung B2 squared over 2G. Solving for Z1, or solving for Z1, or the value of Z1 is 3, HL is 0.24. Yung velocity natin dito, yung unknown, actual velocity. Then, G is the gravitational acceleration. Solving for the actual velocity, we have 7.359 meter per seconds. Ayan. Then, next, solve natin yung value ng theoretical velocity. Theoretical velocity, that is equal to the square root ng 2gh. So, now we have a open tank, free discharge. So, h na malaki is equal to the head of the water lang na 3 meters. So, solve for the value ng theoretical velocity, we have square root ng 2 times 9.81 times 3. Or, velocity theoretical na 7.672 meters per second. And since we have the actual velocity and theoretical velocity, we can now solve for the coefficient ng velocity. So, coefficient of velocity, that is V actual divided by V theoretical. So, CV ay 0.959. Walang unit. Ayan. Then, ayan, no, meron na tayong actual area, meron din tayong actual velocity. So, solve natin si actual discharge. Actual discharge, that is, Q is equal to AB lang naman. Wherein we have A and velocity na dyan. So, simplifying, our actual discharge is 9.103 times 10 raised to negative 3 cubic meter per second, which is our answer for letter A. Ayan. Then next, ang nawawala na lang sa atin is the coefficient of discharge. For coefficient of discharge, we have two way for solving this coefficient. So, di ba? We can solve it by C is equal to Q over QT. Pwede rin naman yung C is equal to CC times CB. And so, kahit alin ditong gamitin mong equation, tama yon. Okay? So, for this presentation, ang ginamit kong equation is yung Q actual divided by the Q theoretical. Wherein Q actual is AV and yung theoretical naman is AO times BT. Ayan, so substituting for the values of area and velocity here, now we have the value of coefficient of discharge na 0.604. Again, that is unitless. So this 0.604 will also be the answer kapag pinag-multiply mo yung CC na 0.63 at saka itong CB na 0.959. So they have the same answer. Actually, kapag CC times CB, mas maikli yung solution mo. You don't have to check for the theoretical area and theoretical velocity pa. I know. Yan, hindi mo na kailangan i-solve si theoretical area. CC times CB na lang. Okay, so isang problem pa, no, bago tayo mag-break. Pero ng break. We have problem number 4. So, a large cylindrical steel tank, 4-meter high, with its bottom on a level ground, contains 2 layers of liquid. The bottom layer is water 2-meter deep. Then the top layer is occupied by a liquid whose specific gravity is unknown to a depth of 1 meter. A 50 millimeter diameter orifice with a coefficient of velocity na 0.98 is situated 1 meter from the bottom of the tank. The jet of the orifice hits the ground by 2.75 meters horizontally away from the vena contracta. What is the specific gravity of the liquid? Ayan, so orifice situated 1 meter from the bottom of the tank. So, kung 2 meters yung water natin dyan, so meron pa tayo ditong 1 meter from the liquid surface hanggang doon. Yun yung distance niya. Then, ito naman, yung 1 meter naman yung depth ng unknown liquid natin sa taas. Then, nilayo ng jet natin, papunta, layo ng jet, papunta dito sa ating vena contracta, that is 2.75 meters. And given tayo ng CV and dimensions ng, or dimension ng orifice. Ayan. So, for this type ng problem, ang hinahanap is the specific gravity of the liquid na nasa taas. So, how are we going to solve for this specific gravity? So, pwede nating magamit yung from the theoretical na velocity wherein we're using the total head produced by the flow or producing the flow. Ayan, then yung solve for the H no, using the equation na pinakita natin kanina. Or let's apply our skills from dynamics, fluid mechanics, and hydraulics. So we have yung 3 concepts. Ayan, so paano natin i-apply dito si dynamics? So we can apply dynamics here sa part na may jet tayo. Ayan, so kaya tinanong natin dun sa attendance sheet ninyo kung naaalala nyo pa ba yung equation nyo for the curvilinear na mga equations? Curvilinear translation. Ayan, or the free flow, or the, ano yun, yung may binabato. Free fall, yung may free fall, ano pa, projectile, no, na mga equations natin. Ayan, so pinaalala natin yan kaninang umaga sa inyo. So, we have also derived equation for the range. So, magagamit natin yan dito sa may jet na to. Kasi, yung, para tayong merong projectile dyan na, yung path ng jet natin is like a projectile. So, we have our highest point at this orifice. Yan yung highest point natin. Then, ito yung na-reach na ng mga distances. Then, the height is 1 meter from the ground. So, we have these two equations derived, for calculating the uh, time and the distances, for the vertical and horizontal. Ayan. So, gagamitin natin yan dito to relate yung velocities natin and the time. Ayan. So, makakalculate natin dito ang velocity is an actual na value. Actual yan, kasi binigay yan by parang experiment. Binigyan tayo ng given distances. So, actual values yan. So, yung y natin, y is equal to the 1/2 gt squared. Or, di ba, galing lang naman yan sa equation natin for the rectilinear translation na um, S is equal to VT plus 1/2 AT squared. But for this equation, the velocity, and since, di ba, curvilinear yan, so we have velocity sa X and Y. And since highest point na to, we don't have velocity na vertical, so that is equal to 0. So cancel out na to. Ang matitira sa atin is 1/2 AT squared. And the velocity that or the acceleration here will be from the gravitational acceleration. Ayan, so jet natin. O kaya siya nagpo-flow due to the acceleration ng gravity. Ayan. So, yan. So, here, since given tayo ng y, ang masasolve natin is yung time. And time will be used to calculate for the velocity since given tayo ng distance na x, kung gaano kalayo yung jet natin from the vena contracta. Then, ayan, gamit lang din ito yun. Dito lang din na-derive itong equation na to na x is equal to vt. Wherein, horizontally, we don't have the acceleration dyan due to the gravity. So, 0 yan. We have vt na lang for the x. Yan. So, recall lang ng mga formula. Okay. So, natin si time and si velocity, respectively. So, we have y equal to 1, equal to 1/2 gt, or yung g natin is 9.81, so meter per second squared. Then, our time is unknown. Okay. Solving for time, we have 0.45 seconds. Then, using this time, we can solve for the velocity using the equation of x is equal to vt, wherein x is 2.75 meters. Velocity unknown, time is 0.45. 2.75 divided by 0.45, our velocity actual is 6.111 meter per second. Actual velocity yan. So, we can use this actual velocity to calculate for the head h. Ayan. So velocity actual, that is equal to the CV square root ng 2gh, diba? So, relationship ng theoretical velocity and actual velocity. So, solving for the h, meron tayong actual velocity na 6.111. Meron din tayong CV na 0.98. And we have the gravitational acceleration na 9.81. So, meaning, ang unknown lang dito is yung head natin, yung total head producing the flow. So, actually, dapat malaking h yan, di ba? So, that is our h. Ayan. So, solving for h, that is 1.982 meters. So, ano ba yung nagko-contribute dito sa total head na nagpo-produce ng flow natin? So, dito sa problem, hindi naman binanggit na closed tank siya. So, meaning, open tank yan. Diba? Hindi binanggit na closed tank. So, open to. Ayan, wala tayong air dyan. So, kung babalikan natin equation for the h na h plus VA squared over 2G plus PA minus PB over gamma. Yung velocity natin, here, since nasa tank, 0, and yung PA and PB natin is 0 na. So, the value of H na total head is just equal to the head of the liquid hanggang sa orifice. But we have to liquids, 'di ba? Dalawa yung liquid natin dito. So, meaning, yung na-solve nating value ng H dito is in terms of the liquid na located malapit sa orifice. So, itong H na yon is head ng water. Head ng water na kinonvert na natin yung nasa taas into a water. Total na head na yon in terms of head ng water plus head ng oil. Ayan. So, 1.982 from here hanggang dito, yan yung head natin. Kapag water lang, hindi dalawa. 'Di ba? Ang liquid natin na water hanggang dito lang sa 1 meter na to. So, ito talaga yung water natin. Di, meron tayong natira na, 'di ba, 1 minus 1.982 minus 1, we have 0.982. So, itong 0.982 meters na to, ayan yung height na para dito sa liquid na to dapat. Ayan. So, we have to convert the 0.982 meters, or we will use the 0.982 meters and yung another height na given na originally 1 meter, no, para mahanap natin si SG, no, using si Saha Baha. O yan. So, SG1H1 equal to SG2H2. Wherein, HG1 natin is yung unknown na liquid na specific gravity. Then, yung H1 is yung height niya talaga, which is 1. Then, HG2 naman, ito yung na ginamit nating base ng liquid, specific gravity ng base ng liquid natin, kung saan nakuha natin si 0.982, which is water. So, we have 1. Then, yung H2 naman is 0.982. So, solving for the specific gravity, solving, we have SG ng unknown natin na liquid na nasa taas ng water is 0.982. So, walang unit yan. So, tama naman kasi yung value ng specific gravity natin na to is mababa kaysa dun sa specific gravity ng water. Kaya umangat siya. Hindi pwede na yung masosolve mo is mas malaki kaysa dun sa water. Kasi, di ba, yung orientation niya, magbabaliktad. No? Kung ano yung denser, yun yung nasa ilalim. Then, ano yung light na liquid, yun yung aangat. Ayan. So, for you to check your answer if correct, kailangan nasunod pa rin niya yung law ng dense water or dense liquid and light liquid. Ayan. So, yun lang naman. So, kapag ginamit mo yung equation na to, na square root ng 2GH, and nasolve mo na yung H mo dun is just the head of the liquid, yung head dyan na masosolve mo is in terms of the liquid kung saan nandoon si orifice. Ayan. So, in terms of the water. Now, kung hindi water yun nandyan, let's say, yung mabigat na liquid, glycerin, di ba, mas mabigat yun sa, sa water. So, kung glycerin yung nasa ilalim, yung H mo dito na 1.982 is in terms of the glycerin. Ayan. So, you have to use yung skills nyo from the fluid mechanics, no, to analyze yung ganyang problem. Ko-convert mo lang naman. O, gamit itong equation natin na derive. Ayan. So, same lang naman. SG siya ng, gagamitin mo yung SG mo ng glycerin. Diba? Dito kasi water So, 1. Yun lang naman for this problem number 4. Ayan. So, bigay pa tayo ng isang sample ng tank na may orifice and we have 2 different liquids na nasa loob. But this time, closed tank naman. Kanina kasi open tank. So, an orifice, 50 millimeter square, with C is equal to 0.6 is situated on one side of a closed tank as shown. Andito yung orifice natin. An open mercury manometer indicates a pressure head of 300 millimeter Hg. Ayan. So, yan yung sa difference in elevation of the mercury here sa ating manometer. So, ginamit yan to calculate the pressure at the air, in the air at the top of the tank. Ayan. So, if the upper 4 meters of the tank is oil and the remainder is water, determine the initial discharge through the orifice. Ayan. So, ito yung mga given sa atin. So, we have 4 meters na depth ng oil natin from the given problem. Ayan. Then, yung sa figure naman natin, we have 2 meters ng water. So, how are we going to solve for the initial discharge ng orifice? So, initially, ang lalabas dito sa atin na liquid is water. Ayan. So, water lang yung, so, kailangan natin i-convert yung head ng oil natin into a water. In terms, dapat tayo sa water. Dapat isang liquid lang muna. Kasi water lang yung lalabas. So, paano natin siya gagawin? Para ma-solve natin yon, we can relate yung mga pressures natin and then the pressure head. But we don't know the pressure of air here inside our tank kasi close yan. Ayan. So, for us to solve for that pressure ng air, we can use the open manometer. So, papunta tayo sa air, gamitin natin si manometer. So, let's say this is our point 1, tapos ito naman si point 2. So, naka-equate tayo kay air. So, air din naman yan here, yung makakalculate mo dyan. So, by the distances or the pressure, summation ng mga pressure. So, pressure ng air is equal to here, at pressure at point 1, which is exposed sa air. So, 0 yon. Ayan. Then, pababa, so, air pa rin naman to. So, 0 pa rin pala. Tapos, at this point, hanggang dito, wag na natin siya isama sa calculation natin kasi cancel lang. Tapos, aakyat na tayo. So, we have mercury dito na liquid. Kung paakyat, negative pressure na unit weight times the specific gravity. Ayan, 9.81 times 13.6 times the distance, which is 300 millimeter. Or in terms of meter, that is 0.3. Then, point 2 natin is the air na yan. So, pressure of air is negative 40.0248 kilo Pascal. Ayan. So, we will use yung relationship ng mga pressure to determine yung converted natin na head in terms of the liquid na nasa malapit sa orifice natin, which is HW. So, are we going to calculate for that? So, solve natin si P at the orifice. Yan. Then, yung pressure natin at the orifice, pag nakuha natin si pressure of the orifice, we can use yung equation natin ng unit weight times the height W. No? So, pressure of orifice dito mararanasan yan is yung pressure dyan by summation ng pressure ng air and the oil and this water. Then, convert natin siya into the head. Sige, solve natin si pressure ng orifice. Orifice is equal to the air na negative 40.0248. Then, plus, since pababa yung motion natin, so plus lang yan lahat, plus the unit weight ng oil times the height of oil, or 9.81 times 0.82 times 4. Plus, unit weight of water times this distance papunta sa orifice na 2 meters. So, unit weight ng water, 9.81. So, calculating for the pressure at the orifice, pressure there is 11.772 kilopascal. Ayan. So, solving for HW, that is the head in terms of the water and oil. So, yung oil natin na-convert na sa water. So, solving for orifice na ito, pressure ng orifice, unit weight times the head. So, we have 11.772 equal to 9.81 times the head natin in terms of water. Ayan. So, head there is 1.2 meters. Ayan. So, here, yung assumption natin HW is mas mataas pa dito sa oil natin. But, from the calculation, that is lower. Hanggang dito lang pala. Dahil yan sa meron tayong sanction. Yan. Kasi negative na pressure yung na-calculate natin dito, di ba? Negative 40.024 ito. Mas mababa yung head natin here. So, this head will be used to calculate for the initial discharge ng sa orifice natin. Kasi in terms of the water na to, so, di ba, water naman na yung lalabas sa atin. Ayan. So, hindi naman oil eh. So, kung oil, dapat i-convert mo yan sa oil. Ayan. So, initially, water siya. So, ito na yung gagamitin natin. We have Q is equal to CaO square root ng 2GH. C is 0.6. Area ng orifice is given from the problem. Sabi, 50 mm square. O, ano ba yung 50 mm square na yan? Ang 50 mm square ba is 50 ganito? O, yung 50 mm square is the given dimension of the orifice. Meron ka daw square na orifice na 50 mm yung each side. So, alin kaya dito yung tama sa dalawa from the given problem? So, yung 50 mm square dyan is etong pangalawa, hindi yung nasa taas. So, dimension yan ng ating square. Meron ka daw square na ang side niya is 50 mm, 50 mm. Okay? So, area ng orifice is 0.05 times 0.05. Multiply to square root ng 2 times 9.81. H natin is yung head, converted na yung oil natin sa water. Okay, 1.2. So, simplifying for the Q will be 0.00728 cubic meter per second. So, this would be our problem number 5. So, may question po ba about the orifice kung paano i-apply yung mga equations sa mga problem?
Wala naman po, ma'am.
Sige. So, if wala na, we can have our break, then babalik tayo ng 1:30. So, balik tayo ng 1:30. You have to take your lunch para busog tayong lahat. So,
Ma'am, hindi na po ba magla-log out?
hindi. Mamaya pa tayo mag-log out after ng second session natin.
Sige po. Thank you po.
Sige. Sige. See you later. Balik kayo.
Thank you po, ma'am.
Okay.
Thank you po.
Thank you.
Thank you, ma'am.
Thank you, ma'am.